So let's begin the second lesson of Professor Hooft.
We'll turn off the air conditioning because it's noisy. And basically,
okay, can I begin? So yesterday I explained that our present understanding of the gravitational sector of physics is very far from perfect. And one of the main difficulties is the occurrence of black holes. So this is a space-time picture of a black hole where time runs vertically in space runs horizontally in more or less arbitrary coordinates. So you could say it's an artist's impression. What we have here was a cross-section. The real world is 3 space, 1 time dimensional, all other circumstances. So what you see here is really a sphere of ingoing matter. But I removed 2 dimensions, so now it's only a line of ingoing matter. And matter goes in basically with something close to the speed of light. And there's so much matter here that according to general relativistic theory, the amount of curvature of space-time caused by that ingoing matter is so much that the speed of light or the light rays that come from this point are being bent in such a way that now we have light going vertically in the time direction. Normally it goes up at 45 degrees. But now there's a bending of the light rays such that light rays go along this line. And this is the horizon of the black hole. Other light rays can go out here, and here the light cone will be normally looking like this, so light would come out. But here cannot, and here all the light cones are pointing inwards, so that no matter where you are going inside. And you're hit by this curved line, which is a singularity of the black hole. Now this is a picture slightly more complex than the usual Schwarzschild solution, because the Schwarzschild solution is static in time. It's just the region above this line, that's Schwarzschild. But this is how Schwarzschild could have started, by imploding matter. And this is a picture that has been around for black holes for a long time. And the problem with it is that whatever went into the black hole is lost forever. It doesn't come out, and it seems to leave no trace whatsoever. Whereas if you react more like a physicist would normally do, the physicist would say, well, if something is being absorbed by an object, that object should be modified by it. There should be some change taking place, and the change will affect the things that come out. So the big question is, do the Hawking particles coming out of the black hole depend on whatever went in? Well, for sure, you know that the mass of the black hole will increase if you let something go in, but the question is, does it also depend on what goes into the black hole? And according to, at least when you follow the book of black hole physics, you would say, no, the final state of the black hole is independent of what went in. But physically speaking, you would say, well, that's against all our experiments. And then you have particles, and particles capture other particles, and modification takes place at every scale. Of course, modifications will be tiny, but they'll still be there. So, the claim now is that this is actually also true for Hawking radiation. But then what I'll do is I'll blow up this region. And blowing up this region will make it look like this. So it means that you have an ingoing particle going in this way, and you're looking at whatever comes out this way. This is Hawking. And the reason why Hawking particles become visible is that the space-time structure outside is so different from the space-time structure here that what is viewed as vacuum by an observer here no longer is a vacuum by as seen by observers here. Why that is so? Well, it has to do with the fact that you are making transformation from these coordinates, so these are the equal timelines, to these coordinates, where these are the equal timelines. So time is defined differently. If you now Fourier decompose a field here into its positive and negative frequency nodes, then positive and negative frequency according to these coordinates doesn't mean the same thing as positive and negative frequency according to these coordinates. So what's positive frequency here would be negative frequency here, and vice versa. And you know when you do quantum theory, you separate out the positive and negative frequencies. You say the positive frequency components correspond to annihilation operators. So those components of the field are telling you what happens if you remove a particle. If you look at the negative frequency, the same components of the field tell you about the creation of particles. So the notion of creation and annihilation is interchanged, and so the vacuum is the definition state where all annihilation operators vanish. But if you don't agree about what annihilation operators are, the observer here will disagree with the observer here about this vacuum state. But this observer will say here, no, some annihilation operators of mine do not vanish, therefore there is something I can annihilate, therefore there are particles of mine. And that's the only annihilation. Fine. As I said, I'm trying to explain that in more detail. It will take at least half an hour or so. I'll postpone it. But the question is, if I let things go in, if I modify the ingoing particles here, what effect would that have on Hawking particles? When you do the calculation, you find there's no effect whatsoever. The Hawking particles form a perfect thermal spectrum. Perfect thermal spectrum, what does it mean? It means that it obeys exactly the Boltzmann distribution, and you see no deviation from Boltzmann distribution. Well, as a physicist, you'd say that can't be right, because things fluctuate, and do the fluctuations of these particles depend on what goes in? And according to the first calculations by Hawking, he said that's not so. The fluctuations are probabilistic random, and the randomness is not affected by the particle. Again, as a physicist, you would complain and say, well, I don't believe that. First of all, there should be physical laws that tell you how things fluctuate, and then those laws should depend on what goes in. So this has been a dispute going on for years, but I think now most physicists agree that yes, this ought to be described by alternate laws of physics. It is our task to figure out what these laws are. And if necessary, we'll make some modifications in what we believe the laws of nature actually are, because part of it we don't know. Part of this question depends on what happens at the Planck scale. Scale where, at which all fundamental constants of nature, like Newton's constant, Planck's constant, and the constant of light, when they're all equal to 1. That scale of nature is still very mysterious to us, but if you would understand that part of nature, you'll certainly find the laws that tell you how things fluctuate. And the question now, can we figure out a little bit about what these laws are like? Well, first of all, you know that the ingoing particles will have an effect on outgoing things in a very simple way. So here, again, you have a picture. Here's an ingoing particle, here's an outgoing particle. The outgoing particle crosses the ingoing particle. Now, it's a simple question of geometry of space-time that you can figure out that particles that went in very early, when you compare those with particles that go out very late, when they go out, they come from the region here where you have a tremendous Lorentz boost. So, in terms of this space-time here, the time as seen by this observer corresponds to a Lorentz boost for the observers here. So outgoing particles are Lorentz boosted to go with very great velocities in that direction. And the later you look at the particle, the closer it is to the horizon, the stronger that Lorentz transformation is, the Lorentz boost is. So now if you have an ingoing particle, you're looking at very high Lorentz boosted outgoing particles. So that means you're looking at particles passing by here with an enormous relative energy or collision energy. So, strictly speaking, the center of mass energy of the outgoing particles you're looking at and the ingoing particles that you assume in the black hole, that center of mass energy blows up exponentially at what time for the distant observer. So very soon that center of mass energy is much bigger than the mass of the black hole itself, much bigger even than the mass of the universe. And now the question is, we have been treating the system as if its particles are not interacting. We're using basically non-interacting quantum field theory to derive this result. That cannot be right. These particles here meet with such high relative center of mass energy that there must be interaction between those things. And you know what the interaction is. If two particles meet with tremendous energy, the center of mass energy is so big that they form a black hole again. So this outgoing thing, this ingoing thing should form a black hole. But now, of course, you end up with mystery. What does it mean? A black hole in a black hole, a big black hole inside a little black hole. How do we handle this situation? And now, there's a simple calculation one can do. And it started off with some work by Eichelberg, Saxon. Write it? Yes. And Eichelberg and Saxon made a remarkable observation. That is, if you have a very fast particle going in this direction, and a very fast particle going in this direction, you can make a very easy estimate of the gravitational interaction between those things. If the particles collide fast enough, they'll have a gravitational effect on each other. And that effect is easy to compute in the limit that the rest mass of the particles are very small. So suppose, take one of these particles and call the rest mass mu, which is much, I'd rather say mu is g times the mass of the particle, but g is Newton's constant. And let's compute the space-time metric generated by the particle with mass mu. If mass mu is very small, it will hardly affect space-time at all. Space-time will be practically flat. But if the particle moves very fast, although its rest mass is very small, its momentum could be very big. Now, having a very big momentum, that particle may have a sizable gravitational effect. The question is, what is that gravitational effect of a particle with small rest mass but very large momentum, going basically with the speed of light? What is the space-time that is generated by such a particle? And this is an elementary calculation anybody can do with some experience in relativity theory, general relativity, and working with the space-time method. And I can show you how the calculation goes. This is a nice little calculation. And it says that if a particle is at rest and its mass is very small, you need to know the structure metric. Omega stands for both theta and phi in the angular direction, but I just abbreviate the transverse part by that expression. I'm mainly concerned about these two things. If the mass is very small, then that becomes dx squared. The dx squared stands for dr squared plus r squared, the omega squared minus the t squared. But I just abbreviate that by dx squared itself. And then there's a correction term, minus 2m over r dt squared. And if m is small enough, then this is written as plus. Oh, sorry, it's a plus, because there was already a minus here, and two minuses, so that gives me a plus. and this is a plus 2m over r the I squared. So when this m is sufficiently small, this is the way the method is affected as a first approximation, and I replace that m by this mu. Actually, the Newton's constant was already absorbed in that, so I'll now call it mu, and being the mass of a very light particle. And now I'm going to boost it. Now, how do you do this? Well, let the forward velocity mu be, well, basically 0, 0, 0, I if you use the complex notation, space-time Minkowski notation. That's just the self-velocity. This is the particle at rest. Well, this is the method of a particle at rest. But let's write the method in a relativistic covariant way. So I introduce the forward velocity. Then this can be rewritten as dx squared minus 2 mu over r, oh sorry, plus 2 mu over r times mu dx squared. That is just basically dt squared in the same notation. And then there's a plus 2 mu over r dr squared. Where r is a space-like component only, so I should call that yeah, this is just the radial distance only. So the radial distance r doesn't change if I boost the particle, let's say, in the z direction. So, oh no, I should say the same better. No, that's not the way I say it. R is the definition, the square root of x squared plus u dot x squared. So, x squared is the invariant x, that's x squared minus t squared. So this is x squared minus t squared, and this is plus t squared. So when the particle is at rest, r is just this. So now I take the same expression, but this expression here is now very easy to boost, to give a big boost in the z direction, because I've written it in a relativistic covariant way. So now I say, instead of choosing u this way, I'll consider mu times u mu as being p mu, the momentum of the particle. But now I can make p mu very large in one direction, and only keep the terms that blow up when p mu becomes large. And then you perform a few transformations. I go from the coordinates x mu, I really find the coordinate y mu, which is x mu, and there's a plus or minus here, x mu plus or minus 2 mu u mu log r. So I go from these coordinates to these coordinates, and then you can see that ds squared can be rewritten as dy plus or minus squared. I can choose any sign here. I need both signs, so I have both. And then there's a correction plus 2 mu over r. But then just you get here r minus plus u dot x squared d, sorry, and plus 4 mu squared log r squared. Let me see something here. Equations now. Oh yes, sorry. There was a d here, and there was a d dot, and d log I squared. This is my log chart. So now I can say that that this is what we call as in terms of which space-time will be flat, and then this is the direction. And now you can say, well, if the particle moves very fast, then at this end of the particle, R is, U dot x becomes very, very large. U is when it's boosted, it becomes a very large vector. Here, the vector U is small, but when you reverse transform it, U will go like some gamma factor times 1 I. And the larger your gamma factor, the reverse transformation, the bigger the U becomes. So this term will rapidly dominate over this, and that means that this will go to U dot x absolute squared. The large square, let's take the square. So the absolute value of U dot x. So now you have to make a distinction. If U dot x is positive, then R is U dot x. And here, R is minus U dot x, because U dot x is negative and R is positive. So when R is U dot x, you see that this goes to 0 very fast. So here, this goes very fast to 0 if I use y plus. Whereas here, I should be using y minus, and then this term vanishes. This term is very small because it goes with U squared. So you take mass small, this term will never be very significant. And so we see that here, in this region, ds squared is dy plus squared, and that's flat space. Here I have ds squared is dy minus squared, that's also flat space. So flat space here, flat space there. But going from here to here, I have to go from y plus to y minus. And now you see that the difference between y plus and y minus is, where is that down? Here. So this was the definition of y plus and y minus. They differ by around 4 mu log r. So log r. So y plus equals y minus plus plus 4 mu. I can also say 4 gm mu log r. Now I'm short-circuiting the argument a little bit to see exactly what happens when you stay very close to the particle. You need to be a little bit careful. But basically what you can say is that when you're very close to the particle, y plus just glues onto y minus, which are making shift. That depends logarithmically on the transverse distance. So r is the transverse distance between the two particles. So if you are very close to this point, then u dot x basically goes to 0. So r just becomes only the transverse distance. So what does this mean? It means if I have a very fast particle, I have flat space before it, flat space behind it, and that's because u dot x is so big that you actually, in the rest frame, you're very far away from the particle. It's being enormous contracted. The space-time is enormous so much, here is so far away from the particle, here is so far away from the particle. Space-time is flat. But where the particle goes, flat space-time is glued onto flat space-time, just twisted it. So what happens now is if you have a particle going in this direction, the outgoing particle goes like this, but then it is shifted about by a shift. And now I can call this x plus coordinate, the light coordinate x plus, light coordinate x minus. Then you see that this shift is a delta x minus, which is basically 4 gm and then u log r. Actually, if n times u mu is of course p mu. So what you see is that the amount of shift that you're generating here is proportional to the forward momentum p, which is also in the u minus, I should say. That u minus goes in this direction. And so what you can see here is a, towards p minus, that the shift in the x minus direction goes proportional to p minus. The shift in the x plus direction goes proportional to p plus. The other particle goes very, very fast. P minus is very fast here, very large here. P plus is very small here. So the particle doesn't shift in the same direction. So you immediately see this is invariant on the coordinate transformations. If we make a lower boost, my light transformation makes x minus much bigger, but also p minus is getting much bigger. So if I use the upper index here and the upper index here. So you see this, you really see this in the relativistic covariant expression, and what it tells me is that when two particles cross with a very large center of mass energy, they're actually both being shifted a little bit. This particle here is shifted in the direction that particle was going, and the amount of shift is given by this expression. Log r is a transverse separation. So the further particles meet each other, the bigger the scattering parameter of the two particles, the smaller the shift is, because the log, because small is far away, the log diverges when the two particles come very close. So now I can give you a, how shall I say it, the plot here. Here a particle moves, again in a different picture. Here I see a particle moving to the right. Here particle 1 moves to the right, particle 2 moves to the left. Here, particle 2, and the shift is a logarithmic function. So what happens is the logarithm goes like this. And it's log of the, this is the transverse direction I. So the log of I diverges and I goes to 0, but then it flattens off quite rapidly here. So the two coordinates are being glued together. What's physically relevant is not log R itself, but its derivative. The derivative log R tells you actually you're making a slight rotation, it's like Lorentz motion. So the particle is rotated a little bit by the slope of this curve, and here the rotation becomes very strong. So the effect of this method is much bigger when R is small, because log R is a much bigger gradient. The gradient itself even is again a Lorentz transformation. So actually it's a second derivative of log I, which becomes physically significant here. That's a tidal force. So two particles, the particles have enormously big center of mass energy. The two particles go like this. They pass each other at the transverse separation R. When the collision has two effects. One is the way the two particles are seen from the other side. How long ago did they pass? That's his log I, but that's just a coordinate choice. Then you see that the gradient of log I tells you the particles will be moving after they left each other in a certain direction. They rotate a little bit in the direction of motion. But the second derivative of log I tells you the one particle exerts a tidal force on the other particle. So when they come too close, they might eventually break up or something because of those tidal forces. We go with the second derivative of log I. Another important thing is that you can write down the Laplacian v squared of log I, which is 2 pi times the delta function of R. See, log I is a solution, it's in 2 dimensions. So, because the transverse distance are only two dimensions, for a black hole we take that fine. So, in the 2-dimensional Laplacian of log I is a solution of the Laplace equation in 2 dimensions with the delta function. So I can also say that